And then some breakthroughs came into being in 1998. Working two-qubit quantum computer was built. Finally, you see the huge leap forward in 1998, and after that, a long gap. Then in 2017, IBM presented the first commercially usable computer, quantum computer. And then onwards, now you see each and every country, maybe China, USA, any other country, now each and every country nowadays are now claiming quantum. They have come up with the best quantum solution, quantum computer. I don't, because I am not still skeptical about this. Anyway, just in 29 September to 2020, if you just go back to the Google feed, you will see that you have announced a commercial 5,000 plus qubit machine. So the race is on. The race is on to just augment the number of qubits. The more number of qubits you can just have in a machine or in your model, the faster it is going to perform, for obvious reasons, because the more the qubit, the more information you can just manipulate. So anyway, that means you are ultimately the target is to increase the number of qubits. That is what is going on. But in spite of that, even if you just go on increasing the number of qubits, things do not settle over there, because other associated problems are still existent. Merely most of the physicists are working in the field of noise, removing noise, or other just how to get rid of the noisy and interference and all these things. But then even the number of qubits also, if you just increase them, obviously you will get a better accuracy or better performance altogether. So it's simple, just to have some idea about what is qubit and why it is different from a classical bit. In a classical bit, you see either on or off, either 0 or 1. A single, you take 1 bit. But the problem is that at any point of time, you can only represent one value. That means either 0 or 1. It is not possible to have both the values together. Rather, you cannot have both 1 and 0 states together using a classical bit. Either you can have a 0 or a 1. Similarly, if you just increase the number of bits to 2 bits, you can represent 4 numbers. But at any time, you can only use or store one value. That is either 00 or 01 or 010 or 11. Not in any position you can just have the combination or any situation where more than one state or one value can be stored or can be used together. So obviously, if you go on increasing, you will get a different number of combinations. Now, vis-a-vis, if you just look at a qubit or a quantum bit, so also it is referred to as a qubit, only single q and then bit. It is also quite used nowadays. So you see, it exists in both the states of 0 and 1. So actually, it is referred to as Kate 0 and Kate 1 and Kate 0. So the beauty is that if you take 2 qubits, for example, if you take 2 qubits, obviously you can have 4 states, but 4 states simultaneously. That means you can have a superposed state of state of four different states together simultaneously. So that is the point of difference between a qubit and a classical bit. So for n qubit systems, you can have 2 to the power n superposition states, and all of them simultaneously available for manipulation and for computation. So that is the main issue over here, but with some different probabilities, obviously, because in normal situation, if you just go for a superposed state, both for example, a 1 qubit system, you'll have a Kate 0 and Kate 1 with equal probabilities, fine. But if you just go on some manipulations, say for example, you allow the system to evolve, obviously these probabilities will change with time. So at times, but even then, with different probabilities per se, all the states will exist simultaneously, coexist simultaneously in a superposed state. So things will be clearer if you just move forward. So if you just look at the IBM Q system or IBM Q-Skit platform, those are visualized. The entire qubit can be visualized in this fashion. So you have a block sphere. It's also referred to the Q sphere, where you can represent the qubit. So if you see, for this case, it is for a 4 qubit system. So obviously we have 16 different combinations or 16 different states. So here you see all the states are with equal probability. This is the measurement of the probability. So all these states exist together with equal probability. So not that only one thing